Yeah, okay. All right, at least we are reviewing the most important part. So the question is, if the Fourier transform m of t is denoted by capital MF, what is the Fourier transform of m of t cos 2 pi f c t? This is very important. So the trick we use here is, we know from Euler's formula 2 pi f c t is equal to half of e to the j 2 pi f c t plus e to the minus j 2 pi f c t. I showed you this result earlier. So this product mt times cos 2 pi f c t can be written as mt times half this. Instead of multiplying by cos 2 pi f c t, we are multiplying by half e to the plus j and e to the minus j. Then I just take the m of t inside and leave the half. And then I look at the Fourier table, what happens when I multiply a signal by e to the j2 pi f c t. And that's connected to the frequency shift. See, if the Fourier transform of small g is capital G, what is the Fourier transform of small g multiplied by e to the j2 pi f0? So if you have a plus exponent here in this fashion, this becomes minus. If it is minus, it will be plus. So frequency shifting property is used here. And the conclusion is, when you multiply m of t by plus e to the j2 pi fct, e to the j2 pi fct, the Fourier transform become capital M f at f minus fc. And then if you apply the same thing, minus fc becomes plus fc. So this is very important. The modulation property of Fourier transforms. Basically, if you know the spectrum of a time domain signal, that time domain signal multiplied by cosine wave is basically the spectrum of the time, this signal shifted by minus fc and plus fc. So in the frequency spectrum diagram, if this capital M has a particular shape, say triangular or rectangular, after modulation you will see two triangular shape or rectangular shape, one around fc and one around negative fc. I'll show you a diagram when we actually go to amplitude modulation. Okay, now there are some more stuff to learn. You guys learned about linear time invariant systems, and there are those definitions. What do we mean by linear and what do we mean by invariance? I used to give the definition and do some examples, but I don't think they are important because those are like really from signals and systems. But at least I want to mention what is linear. By linear we mean, so you have a circuit or system. Let us say you input x1 t and you get y1 t as the output. Let us also assume when you input x2 t, you get y2 of t. The question is, what will you get when you input x1 plus k times x2? So I am complicating things. I am using addition, but I am also multiplying one of them by a scalar. If the output is y1 plus k y2, then your system is linear. Okay. So in electrical engineering, in fact, in most engineering, most of the time we deal with linear systems, linear circuits. But you should also remember, particularly in communication, there is one crucial place where we love nonlinear system, and it will come in maybe today or in the next lecture. Okay, so we also like nonlinear system, but most of the time we love linear systems, and the reason is the analysis or the mathematics for nonlinear system is very difficult, almost impossible. That's why engineers love linear system. So even when real world systems are going to be non-linear, we make sure they are approximately linear and then analyze it assuming linear. Now, what does time invariant mean? Time invariant means when you input x of t, you get y of t. The question is, what happens if you input x of t minus 3 seconds? If you do get y at t minus 3 seconds, in other words, the time shift is exactly the same, then we say time invariant system. Now, this is very important. Almost all the system we use are exactly time invariant, because otherwise we will be in big trouble, particularly like in mobile communication and in computer communications too, because you guys know we deal with digital systems. So you have rectangular pulses. So you have like, let us say after coding, you have an arbitrary pulse, short pulse. There's an interval and long pulse. And if that delay in the next pulse is, you can think of like a time shift. So you have one pulse, there is a delay and then another pulse. If that time interval changes at the output, the meaning of your digital signal totally changes. So you guys probably heard about pulse width modulation and things like that, just roughly. So if the system is not time invariant, you could input 1011 in a circuit and the output could be a different binary number and the system completely screws up. So time invariance is very important. All right. Then in signals and systems, you guys learned about the definition of these things, the mathematical definition, and then they sometimes gave you a system's transfer function and ask you to prove it is linear time invariant, and we are not going to do that. We are just going to look at the question. So from this point onward, you have to assume if I talk about a system, it is linear time invariant. Okay, I am not going to say every time we are talking about linear time invariant system. And also in signals and systems, you guys learned about impulse response of a system and the transfer functions. And usually these things are useful only for linear time invariant system. So just assume everything is linear time invariant. So the impulse response of a system is given by this. So you guys know what is impulse response. Impulse response is, you have a circuit. If you input the impulse function delta t, what is the output? So in this case, it is the decaying, e to the negative 3t will start at 1 and then it goes to 0 as t goes to 0. But this is the unit step function, which means is when t is negative, this is 0. So this you should imagine like vertical axis, horizontal axis, nothing before t is equal to 0. It is horizontal at 0. Suddenly it jumps to 1 and then it decays. Okay. All right. Now for this question, I have given you a Fourier transform pair, which was not in the handout or the 8 sheet I have there. So if you have to use a new transform pair that is not in the 8 sheet, I will give it to you. So basically, the pairs given were e to the negative at ut becomes 1 over a plus j to pi f. E to the a absolute t becomes 2a over a square over 2 pi f. The Fourier transform of this is this, Fourier transform of this. Okay. So here there is some review from signals and system. So impulse response is denoted by small h. The Fourier transform of the impulse transform is called the transfer function. So what is capital H? It is the Fourier transform of small f. So g of t becomes y of t. This is the usual notation. And the Fourier transform of small g is capital G of f. Fourier transform of small y is capital YF. The relationship between GF and YF is given by YF is the product of HF times GF. In other words, the Fourier transform of the output is transfer function multiplied by the input Fourier transform. But what is transfer function? Transfer function is the Fourier transform of the impulse response. What is impulse response? It is what you get here when you send an impulse at 0, the delta t. Okay, all this is revision from signals and system. Find the output for the input signal GT. Give you an answer in the form of an integral in time domain. Okay, so this is another revision. If you are talking about the Fourier transforms or in frequency domains, output Fourier transform is given by this. But this is about time domain. You know the impulse response, which is the output for impulse function delta t, but part A says find the output if the input is GT. You guys know from signal system, the output is actually the convolution of h of t with your input. So let's see if that's what I have. Yes, look at here. Y of t is the convolution h of t. And someone pointed out, I think last term, if you like, please change this to minus infinity to plus infinity. I put 0 here because our signal doesn't, actually it is better. So guys, please change this to minus infinity. I will change it and post it again. Okay, it's kind of dangerous to put 0 here because you could make a mistake. However, it doesn't really matter because I am not going to ask you to do convolution. Okay, so it's not that important. Define the transfer function of an LTA system. Yes, that you know. Transfer function is the Fourier transform of impulse response. Find the transfer function of the given system. So h of t is given as this function. So the transfer function is the Fourier transform of this, which is right here. You have to plug a is equal to 3. So if I put a is equal to 3, I get 1 over 3 plus j2 pi. These are like baby questions. Okay, I'm just reviewing. Write down the equation that connects the Fourier transform of the output to that of the input. Okay, you know this. YF is HF times GF. Suppose the Fourier transform of G of t is given by this. Find the output Y of t. So you guys know how you did this in signals and system. Y of t is actually the convolution of h of t with g of t, but we usually don't do this. We would rather work in the time domain. So I first calculate the output Fourier transform, which is h of f, which I already calculated, multiplied by g of f. And then I simplify this, I get this. And then I take the inverse Fourier transform because I already gave you that pair. Where is that? It's right here. So I use this and I figure out, I compare this expression to my answer and figure out a is 3. And then I just plug it in this expression and I have to adjust for 2a. I think because in my answer it is 1, so I have to divide both sides by 2a. So that's how I got this number. So from this one, going to Y of t is a very good exercise in going back and forth in Fourier transform very quickly, because often you have to multiply by constants, which most people are okay. Sometimes when you have to divide by a constant, people get a little bit worried, okay, because in the original pair there is 6 sitting here, but in my answer there is no 6, so I divide by 6. All right, guys. Okay. Another thing you guys have to know is when we have a system, its transfer function is given, you need to worry about the amplitude and phase response of that system. So what is amplitude response? Is you take the transfer function and write it in the polar form and look at what is sitting for the amplitude. That is, in general, the magnitude of that complex number will be frequency dependent. It may depend on f. And then you look at the angle, and the angle, what you do is you just take the j out, leave the j out, and think of what you have. It may be a function of f. And I'll talk about why this is important in a moment, but here is an exercise. Sketch the amplitude and phase response. So I have given you the solution for the first one. So the amplitude, to calculate the amplitude response, I need to write this in polar form. When you write in the polar form, what you have here is the magnitude of the complex number. The magnitude of a fraction is the magnitude of the top divided by magnitude of the bottom. Magnitude of the top is 1, and then I get square root of this square plus this number square, which is, this is all from complex numbers. Okay. The angle of a fraction is the top angle minus the bottom angle. But the top angle is 0, so it's basically the minus of the bottom angle. The angle here, angle of this complex number is tan inverse this number divided by this. You can imagine that in the Argand diagram, the y height divided by the x height. So you have tan inverse 4 pi f over 3, but it's negative because we are subtracting from 0, okay, because there is no angle for this. So we have this. Now if you plot this, roughly speaking, this expression will be maximum when this is a minimum, and this is a minimum when f is 0. So when f is 0, it's at the peak. On either side it decreases because it is a square. It doesn't matter whether it is plus or minus, it is symmetrical. But this graph doesn't look symmetrical because I cut it off here, but in reality it is perfectly symmetrical. The MATLAB cut it off. Okay. Now the graph of this is a scalar version of tan inverse x multiplied by, sorry, a scalar multiple of tan inverse x but multiplied by -1. So if you remember tan inverse x, it goes like this. From negative pi over 2 to, this is plus pi over 2, this is negative pi over 2, this is the origin, it goes like this, but this is negative of this, so the orientation is, so okay. Just you need to have a rough idea. I'm not really going to ask you to sketch this in the exam. Okay, now here is something important. I think this is the last topic in this lecture, then we will start the AM and go a little bit. Are you guys okay so far with all of this is okay? All right, you have to stop and ask me questions. Okay, I don't mind you guys interrupting me. Okay. You guys know that after modulating using amplitude modulation or frequency modulation, we are going to transmit. So it's going to go from your the radio station to your car or your home, or from cell phone tower to your cell phone, to your mobile phone, or from your mobile phone to things. So if you are communicating with a spaceship that is traveling to Mars, then it has to travel through the space. But certain things could happen in this transmission. We don't really have to worry much about when we transmit through the space, because it just decays according to the inverse square law, because you know all radiation, the intensity decreases with the square of the distance, inverse square law, you guys know. Other than that, there are no artifacts. But particularly with your mobile cellular phones, the signal from your cell tower, before it comes to your phone, particularly in like a downtown Toronto scenario, big city, the signal get reflected in the tall buildings, and you will receive multiple signals, 3 or 4 different signals. One signal will arrive at your phone very fast, the other one get reflected from the building and comes, another one will get reflected from the earth and comes. So like 3 or 4, and the time delays will be different because the one that get reflected will be delayed by microseconds or picoseconds. So the effect is the addition of all of these, and the addition of these is not simple inverse square delay. So because of that, we really have to worry about something called distortionless transmission. So eventually when we transmit these mobile signals, we don't just amplitude modulate and send. There is a lot of things going on because of the digital communication. So what is important is the shape of the signal. So for example, a typical digital signal after demodulation may not look like the diagram I have given you, but it may look like a small rectangle followed by a higher rectangle with a long thing, then a small rectangle, maybe then there is a narrow rectangle with a height. It could happen, and that shape is important at the receiver. Like it could get crunched vertically, it doesn't matter, but it should not get crunched horizontally. The time is important, timing, but vertical, the attenuation is not a problem. Just like inverse square law just attenuates the amplitude. So this is very important. So whenever the shape is preserved, you guys see this, but it is attenuated vertically, the digital communication systems works fine. But the time, if this length is 7 microseconds and this is 8 microseconds or 9 microseconds, we are screwed. Because of that, we have this concept called distortionless transmission. So listen to me very carefully. Whenever the shape remains exactly the same, nothing changes horizontally, but vertically the thing is attenuated, that's fine. When that happens, we call this distortionless transmission. If this property is not there, for example, something happened in the time domain, this get delayed by 5 milliseconds, this get delayed by 7 milliseconds, this will be different, then that has distortion. Vertically, if every instant get crunched by the same amount, like 1/3 or 3/4, we are fine. But if this triangular portion get multiplied by half, but the rectangular portion get multiplied by quarter, two different numbers, then we are screwed. So distortionless transmission means constant attenuation and no screw up with the time delay. A time delay is always the same. Okay, so now there is another way of phrasing this. What I explained is like the common sense explanation, but we have to get more mathematics. And we are now going to prove what I described actually translates into a mathematical condition, and that says when you take the the amplitude response and the phase response, the condition I explained in plain English translates to two conditions. The amplitude response must be independent of frequency. That means h of f, absolute h of f, magnitude of h of f should be constant. There shouldn't be any f. And the angle response or phase response must be linear in f. So what I just explained in time domain translates into the following in the frequency domain. Distortionless transmission means h of f is constant and theta hf is a linear function of f. And we are going to prove that using our knowledge of Fourier transform and show that for distortionless transmission, amplitude response of the channel must be flat, meaning it is a constant. The phase transform must be linear in F. So what I am writing here, starting here, is what I described in English first. So in the time domain, an attenuation is fine and constant time delay. So let's say the time delay is TD. So I start with this, and from this I am going to derive these two results. Amplitude response is A and phase response is minus 2 pi f TDF, and you can see it is linear in F. Okay, so what do? I take Fourier transform on both sides. The Fourier transform, this is y of f. This is a constant, so I write the constant because of the linearity property. So if I know the Fourier transform of small g is capital G, then the Fourier transform of this would be g of f time e to the j 2 pi f time delay. This is from the properties of the Fourier transform. And then here I also know from signals and systems, y of f is h of times g of f. So from here to here, it is signals and system, or what we reviewed, but this was obtained by the Fourier transform of this. Now I want you to look at this equation, and you can cancel g of f. If you cancel g of f, you get h of f is equal to 8 times e to the minus j2 pi ft. So this line was obtained from this by cancelling g of f. And if you look at this, the magnitude of this complex number, this is already in the polar form, is A, and the angle is minus 2 pi f TDF. So the distortionless transmission means the amplitude response of the channel is constant and the phase response is linear. So if you plot them against frequency, 2 is just an arbitrary number I chose. Amplitude response if A is 2, it's flat, and phase response is negative linear function. Alright guys. Now one more question. I think this type of question appeared several times in the past midterms. So there are 4 different transfer functions were given. You are supposed to find out which channels allows distortionless transmission. Okay, so these are the transfer functions of different channels. So let's first consider the first one. If you take the amplitude of this, magnitude of this complex number, it is magnitude of this divided by magnitude of this. Magnitude of this is simply 2 pi f. Magnitude of this is square root of 9 plus 16 pi square f square. Clearly, the magnitude depends on the frequency. So this is not going to be allow distortionless transmission. This is out. If you look at the last one, the magnitude is 4 plus 36 pi square f square, square root of that. Again depends on the frequency. So these two are out. Let's consider second one. The magnitude is 5, and let's consider this one. The magnitude, to find the magnitude of this is, we can write this expression as e to the 5 times this, therefore magnitude is e to the 5. So the amplitude response here is flat at 5, the amplitude response here is flat at e to the 5. So these two are good candidates, but we also have to check phase response. Phase response is minus 4 pi f, which is linear in f. Here, if you look at here, minus 4 pi f, which is linear in f. So these two channels have flat amplitude response as well as a frequency response that is linear in f. So these two are the transfer functions of distortionless channels, whereas these two will distort. So if your channels are like this and this, and if your mobile communication is going through this, you will encounter a lot of problems. Okay. Now there are more questions. What I will do is your TAs will solve some of these problems. Please listen to me carefully. Before the exam, if any of these problems are important for the midterm, I will go through them. But please don't email me saying where is the solution for this. Okay, because some of them are not that important. Although ideally speaking, if signals and system, if you got an A plus, this is a good test. If you got A plus in signals and system, you must be able to handle 13, 14, 15, 16 and 17. But please try them, and your TAs may do one or two of them, but they are not going to do all of them. If they are important, I will do them after I finish the material for the midterm when we have time. I think we are going to have plenty of time this year. And in fact, I was planning to go for 2 hours today. I think I can now go to the next lecture, and I will probably go like 45 minutes and stop. Are you guys okay so far? Any questions? You guys are okay? All right. One more thing, you guys may be surprised. I mean, how come we are like going ahead of schedule or something like that? Part of the reason is I have typed up everything in a regular year before pandemic. Most of this stuff I have to write down on the board. So everything I write on the board is now typed up. So basically, if I want, I can go like double the speed, but I am actually slowing down. Okay, guys. All right. So let me bring up the AM. I have to look for it. Where is? Okay, so we are going to start amplitude modulation. I already explained you the reason we use amplitude modulation is efficient power radiation with antennas of reasonable size. Also, we often use frequency diffusion multiplexing, which I talked about that. Now there is another usefulness, but that is only in FM. So let's ignore 3 for the moment. And there is a fun application of modulation in outside of communication. I already mentioned that is in electronic keyboards to get those very fun effects. All right. Now amplitude modulation itself, unfortunately, there are 4 types, but thankfully for you guys, because this is going fast, accelerated, even though we have time, students don't have plenty of time to absorb the material. I like to skip certain things. So 3 and 4 are out. Single sideband modulation and vestigial sideband modulation I am not going to teach. So it's only double sideband suppressed carrier modulation and large carrier amplitude modulation. We are only going to talk about these 2. Okay, so this I am not going to teach, and these 2 will not be in the midterm. Okay, so the first topic is double sideband suppressed carrier modulation. I will often use the abbreviation DSP-SC. Okay, what is DSP-SP? So you have a message signal. By the way, here it says modulating signal, but most often I will say message signal. So what is the message signal? Imagine 680 news and someone is reading the news, and it's an audio, the microphone converts it to an audio signal. Maybe they did some amplification, and the message signal is shown here. Okay, and then we have a carrier signal, and I didn't really plot that here. It is usually okay. So for 680 news, the message signal is actually for all radios. Message signal bandwidth is between 50 about 50 hertz to 15 kilohertz. You guys know that the audio signals 15 kilohertz. Well, sometimes I would say 20 kilohertz, so maximum 20 kilohertz. The carrier signal for 680 news is 680 kilohertz. The total AM band in the radio, you can watch it in the car radio, is about 450 kilohertz to 1500 kilohertz. So 680 is like kind of in the middle. Okay. So always keep that in mind. This FC is much higher than the highest frequency in the modulated signal. So here I have given you the picture that we had. So basically, oh, what did I do? Sorry, I was talking totally different. Okay, sorry guys. This is the message signal. This is the modulated signal. Okay, sorry, we completely mixed it up. This is the message signal really expanded horizontally, audio signal. Then there is high frequency carrier signal, and what we do is we multiply the carrier signal by the message signal. Okay, it is very, very important. Anytime I say DSPSC, you take the carrier signal and multiply it by the message signal. This is the expression. Okay, so very simple. You take the message signal, you take the carrier signal and multiply them. That's it. And when you do that, if this is the message signal and you have a red signal that I showed you the first lecture, multiply, you get this. So this is the modulated signal. This is what is connected to the antenna and then get transmitted. So the message signal is embedded in the envelope of the carrier. So terminology, this thing is called the envelope. Okay, now you see already there is a minor issue. The audio signal was of this shape and that shape is right here. So in the receiver, we are going to demodulate this and recover this based on this envelope. And some of you may know this, how to do this. All you have to do is send the received signal through a rectifier and it will get rid of the negative parts. You guys know how to rectify AC signal and get a DC signal. And if you have a capacitor, then when it goes here at the peak, it will start to decay and it may not come to zero quickly. It may go somewhere here and meet the next peak a little bit below the peak. So it goes like this, and then instead of falling to the ground, it may go like this. Then it goes to the peak, comes back, start dropping from the peak. I will show you the diagram later. That will happen if you have the appropriate capacitance. If your capacitance is too small, from the peak it will fall all the way down to zero before rising. But you can adjust the capacitor so that from the peak it decays slowly and meets the next peak a little bit down from the peak. Then it will go up the peak, then start dropping again, and it might meet the next one. So we can easily recover the envelope using a diode, a rectifier. That's what we do in all simple, very cheap receivers. Okay, and there are more sophisticated systems. Now, by the way, that is called envelope detection, and we will go into the detail. However, you immediately see a problem here. Here, the audio signal is negative, but the envelope here remains here, because what happens is this is negative. All that happens to the carrier signal is the carrier signal change phase. So here everything is positive. A signal that is constant amplitude got modified according to this signal because you are multiplying by this. But at this moment, you begin to multiply by negative numbers. So this whole expression earlier, instantaneously, this had a positive number. So it's like, let's say 0.5 cos 2 pi f t, 0.6 cos pi f t, 0.7 cos pi f t, blah, blah. And then all of a sudden it is minus 0.5 cos omega ct. So there is a phase change. Everything gets flipped. But that doesn't really bring the envelope. In fact, the envelope went here. You could say this is the envelope, but we cannot use a diode to figure this out. This one. Diode will give you this, this, and this. So your recovered audio signal will be like this, and then it will get screwed up here. Okay. So DSPSB has a minor issue in detection or demodulation, and we will talk about that. Okay. Before that, what is the Fourier transform of this? Now we already proved this like half an hour ago. If you know the Fourier transform of m of t is capital MF, mt multiplied cosine pi f is the same spectrum shifted to fc and minus fc, and why did I multiply by, and there is a half there. Please remember this. We proved in the previous lecture slide there is a half, and where did the AC come from? Because there is the AC. I multiplied by this. So the spectrum of DSPSC is right here. It is the spectrum of the message signal shifted to FC and negative FC and multiplied by half, and then there may be a constant sitting for you from the carrier. So you really need to know this, and also it's better to visualize this in a diagram because that's easy to remember. Let's see if I have a diagram. Yes. Don't read this, I already explained you. So take a message signal of bandwidth B. I told you bandwidth is not 2B. We just read this. This is the message signals spectrum. Modulated signal. The modulated carrier is basically this shape, but multiplied by AC and then halved. So AC times A over 2. And then it will go sit at FC and negative FC, but horizontally no change. So if this gets shifted to FC, then this will be FC plus B, this will be FC minus B, and you can figure out the numbers here. Now, if you look at the bandwidth of the modulated signal, it is 2B. Okay, this is very important. The bandwidth of the message signal is B. That of the DSPSP is 2B, because I already told you how to measure the bandwidth of signals like this from here to here. You can just ignore this. And then this part becomes this here, and this part becomes this. This is called the upper side band. This is called the lower side band. All right. So in the transmitted spectrum, you have lower and upper side bands. Now you can immediately see that if FC is less than the bandwidth, this is going to cross over the vertical axis. This will cross over vertical axis, and things are going to get mixed up. But this is not a real issue because audio frequencies, maximum frequency is 20 kilohertz. Radio usually have carrier frequency starting at 450 kilohertz. So it's not, this is in practice, this is much higher than this. So we don't usually worry that much about this. One important aspect is, if you look at this expression, all of this came from this theorem, this capital M came from this spectrum of the message signal, and the contribution of the carrier is just multiplying this by this constant. The cosine part did not really. Now you guys have to understand this in itself has a spectrum. The spectrum of cosine is half on this side, half on this side. So here it will be AC over 2 and on both sides, and we don't see that here. You don't see a separate signal standing out here, AC over 2 and, sorry, A over 2 and, is it AC? AC over 2 and AC over 2. We don't see that. So it is very important. Carrier frequency does not participate in the spectrum of the DSP-SP signal. Okay. The only contribution is this constant going and multiplying. But you don't see the spectrum of this. The spectrum of this is 2 spikes at AC over 2. 2 spikes of amplitude AC over 2. One at FC and one at negative FC. We don't see that. Okay, that's important. All right. Let's see. Now, so usually when this happens in the radio station, the audio signal spectrum may go from 50 Hertz to, let's say, 20 kilohertz, because 50 kilohertz is very small. We can say it starts from 0 to 20 kilohertz. So the spectrum may look like this. This is the transmitted spectrum. However, traditionally, there are two reasons. One is we need to calculate what proportion of the power of the message signal actually goes into the transmitted signals and so on. We need to have some idea of how much energy we are wasting and so on. Those calculations are hard to do if we consider range of frequencies like from 0 to 20 kilohertz. So to simplify, we consider very artificial situation where we assume the radios are transmitting only one signal, like one frequency. What happens if this is just a 1000 kilohertz signal, one single signal? They don't do that, although it is interesting if you live in rural areas. Okay, let's come back to Toronto. In Toronto, most radio stations operate 24 hours an hour, 24 hours a day. But in rural areas, radio stations sometimes start at 6 o'clock in the morning and then they sign off at 12. So most people get up like at 5 o'clock and take shower or something, and they may be listening to the radio. They can't wait for the transmission to start. So sometimes they start the radio 10 minutes earlier, like 5 minutes to 6. And the radio stations want to tell the people, don't worry, we are here. We will start at 6. So what they do is they put a whistle. You can hear the whistle from like 5:45 to 6. Before 5:45, it will be silent. Radio station become alive at 6, but for the 15 minutes before that, the station will transmit a very annoying sound. And what is that sound? A single frequency. Like it could be like 500 hertz signal. It's a very annoying whistle. And at 6 o'clock, someone will come and say, oh, good morning, welcome, and so on. Okay. And that is called tone modulation. So what is tone modulation? Instead of using a range of audio frequencies like someone speaking or singing, playing CD, we generate a sinusoid waveform or cosine waveform of single frequency using an oscillator and then modulate it. That is called tone modulation. So in tone modulation, this m of t is equal to cosine 2 pi fmt, f sub mt, that is that single tone. And we are going to do some math with that. So we can calculate efficiency and so on. So that is called tone modulation. So message signal is there is an amplitude AM cos 2 pi FMT. Okay, F sub FT. Carrier is AC 2 pi FT. Then we need to calculate the spectrum. So what is the spectrum of this? The first question. From the Fourier transform table, spectrum of cosine is half here and half here, but there is AM, so we get a delta function of magnitude AM over 2 here and AM over 2 here. What are the frequencies? FM and negative FM. This is from the Fourier transform. Then we apply what we learned for general modulation and get this figure. So if you go here, for each of these frequencies get shifted to from here to here. So if you take a single frequency, that frequency should be shifted to FC as well. So if this is FM, it will be FC plus FM here and FC minus FM here. So that's the first FC plus FM, FC minus FM, and also minus FC plus FM, minus FC minus FM. So for tone modulation, remember, another way of looking at this, the modulation shifts the original frequency to be around FC and negative FC. The original frequency is at FM and magnitude AM2, so it gets shifted here and here. Modulation doesn't just shift, it also halves it. Remember the theorem? Well, we have a half here, but more importantly, let's visit the, that's in the previous lecture slide. Okay, so that's where this AM over 2 become AM over 4. Where did the AC come from? That is just a constant in the carrier frequency. So if this is AM and this is AC, you have to memorize this is AM over 2 because that is the Fourier transform of this guy. And the modulation basically shift the frequencies to FC and negative FC and then halves the spectrum. So it becomes AM over 4. Where did the AC came from? It's just a multiplicative constant. Okay. So this is the spectrum of tone modulated signal. Let's see. Okay, so I think let's go a little bit more and then maybe we can stop. Now, earlier I told you about a quick and dirty demodulation scheme that is called envelope detection or rectifier receiver. Now I also briefly mentioned we have an issue with that. If we were to just put a rectifier and capacitor, it will go like this, trace this amplitude, and at this point it's not going to trace this, it will trace this. But there is a more sophisticated detection scheme which is basically based on trigger identities, which works perfectly fine, and that is called coherent detection or synchronous detection. So right now we are talking about demodulation. What happens at your radio in the car? Okay, so demodulation, modulation at the radio station, demodulation at your radio receiver. The transmitted signal DT arrives at the receiver. So in those days, car stereos also had an antenna and they received it through that antenna. Nowadays they have figured out the whole body of the car or part of the body can be the antenna. They have figured out stings, so you don't see the antenna, but somehow the signals arrives. So you can see this is the expression for the DSP-SP. Okay, message signal multiplied by the carrier signal AC cos 2 pi FCT. In synchronous detection, what they do is they produce the exact carrier signal, which is cos 2 pi FCT, using an oscillator in your radio and multiply the received signal dt by cos 2 pi fct. So this may be a little bit confusing. The arriving signal is ACMT cos 2 pi fct, but you multiply it by cos 2 pi fct again. And if you substitute this here, it becomes AM cos square 2 pi fct. Now remember I told you last week cos square x is equal to half times 1 plus cos 2x. So I used the tricky identity that is called cos square x is equal to half times 1 plus cos 2x. So this square disappears, 2 pi fct becomes 4 pi fct. Now if you multiply it, you get AC over 2 m of t plus AC over 2 mt cos 4 pi fct. So you can see your message signal is there. It is just multiplied by this constant. But we have to get rid of this signal. This is, if you really look at it, this is the DSPSB at the carrier frequency 2FC. Okay, but we are not interested in that. We want to get rid of this. But we know the spectrum of this will be around 2FC because we know the spectrum of DSPSB. So the spectrum of this, or the frequencies from here, will be around 2FC. This is like between 0 and 20 kilohertz, and this will be 680 multiplied by 2 kilohertz, like 1300 kilohertz. This will be around 1300 kilohertz. Here the maximum is 20 kilohertz. So what we do, we send it through a low pass filter. Okay, and I didn't even bother with these things. Okay, so after multiplying by this, the signal is this plus this. I think I just wrote it but put a bracket saying this is 2 pi c, and then I am deriving the Fourier transform of this. The Fourier transform of this time MF, and then this will be half of this, and the spectrum of this shifted to 2FC and plus 2FT. Anyway, this expression is not very important. What is important to realize is this spectrum is around 2FC. So if we have a low pass filter, that will get rid of this. Remember, low pass filter that only leave low frequencies to go through. So here is the how do you call this, a diagram for synchronous or coherent detection. This is the arriving modulated signal. You multiply it by the same carrier, and then the result is sent through a low pass filter with a cutoff frequency just outside 20 kilohertz. Or at 20 kilohertz is okay, because most AM radio stations don't worry about high fidelity. So they think their signal ends at 15 kilohertz. They don't really worry about anything other than higher than 15 kilohertz. So maybe they will put a filter at 17 kilohertz cutoff. That will only give you this. Alright guys? Okay. Now, there is a small danger in coherent detection. And the danger comes when, remember, your radio station is, they are rich, they will have very good oscillators, so they will somehow multiply the message signal by a 680 kilohertz signal. The local oscillator in your radio, if there is a problem with that oscillator, remember, you have to multiply this again by cos 2 pi fct. There may be two problems. Your oscillator may deviate tiny bit in frequency. Instead of generating 680 kilohertz, it may go to like 690 kilohertz or 670 kilohertz. And that will screw up your message, the demodulated signal. Another thing that could happen is, here we are assuming this local oscillator is perfectly synchronized in phase with the carrier frequency. For example, your local oscillator could generate exactly FC with a phase angle like 2 pi FCT plus 45 degrees, plus 20 degrees, plus pi over 8. So the local oscillator could drift away from the carrier signal by frequency or by phase. And we will just look at what happens in those two cases and then stop today's lecture. So this is called, this is a very bad word, non-synchronous detection, but it's actually synchronous detection where the local oscillator has problem. The local oscillator at the receiver may not be perfectly synchronized to the carrier. Transmitted signal arrived at the receiver. What if the local oscillator generates 2 pi Fc plus delta Fct plus phi. So phi is the phase shift and delta Fc is the frequency shift. Now, this is very hard to analyze. So what we do is we will first analyze what happens with one of them being 0. Now we will assume only frequency shift happens. We will observe what happens. And then we will consider the case only the phase shift happens. So let's see what I did here. Wow, did I do all of this together? Yeah, I didn't actually do it separately. I included delta Fc and delta Fi. Okay. Now, this is cos A times cos B. And remember that formula? That becomes cos A plus B and cos A minus B. And you can verify these cancellations. Basically, what happens is you get this and this. And then I simplified it here and this one. So I think in the next step, I think it is here I separate the two cases. Okay. So if we look at this, this is still around 2 pi, this one. The first part is still around 2 pi FCT. So when you send this after the multiplication, send it through the low pass filter, you will only get this part, second one. So this is a high frequency. Low pass filter will give you this. So earlier we didn't have this cosine 2 pi delta phi thing. We get AC over 2 MT earlier with perfect synchronization. Let me see. Yeah, AC over 2 MT. Now we are getting AC over 2 MT times this cosine terms. Let us consider two cases where this is not 0 but phi is 0. So if phi is 0, you get your message signal multiplied by cosine 2 pi delta Fct. So, but remember, let's also assume the drift is constant, like it is producing, let us say 10 kilohertz higher. Instead of 680, it is producing 690. That means this is 10 kilohertz. So this is a cosine signal with 10 kilohertz frequency. So your message signal will flutter at the audio frequency, like it will, you will hear some artifact. Basically your message signal will oscillate because this is a cosine signal. But how that oscillation is heard by the human ear will depend on how big the delta Fc is. If we have time, we will discuss that next time, because you have to understand, for example, if this delta Fc is like 2 hertz, not 2 kilohertz, 2 hertz, then you will really hear a change in the volume. You will, it's like an older person shaking voice, like tomorrow it will rain or something like that. That is if this is like a low frequency. But if it is like 10 kilohertz, 10 kilohertz itself is an audio signal. So you may hear a whistle on top of the news reader. Okay, but let's not worry about it. All you have to know is if phi is 0, you get an oscillating signal. Now what if this is 0, that there is no shift in the frequency, it's exactly 600 kilohertz, but this is like 30 degrees. So you have cos 30 degrees, which is a constant. So which is a constant attenuation. So instead of receiving this, you are getting a fraction of this. But that's not a problem because you can always turn up the dial, the volume dial. So this part is usually not a problem because this is 0. So you message signal is multiplied with cos phi. If phi is 45 degrees, it's cos 45 degrees, which is 1 over root 2. So your message signal is going to be divided by root 2. It's basically it gets attenuated, which is not a big deal. But what if phi is 90 degrees? If phi is 90 degrees, then cos phi is 0. Cos pi over 2 is 0. You multiply the message signal by 0, you don't get anything. So your radio will be silent, no signal. All right, guys? Okay. So I think we are going at pretty good speed, so I don't have to finish this because there is one more lecture and that's all you are going to get before the midterm, and there is plenty of times. Okay. All right. Any questions so far, guys? All right.